Well, hello everyone. Welcome to this first day of this new initiative called the Africa Scholars Meeting. Allow me to share my screen to just make a quick introduction. Okay, so well, welcome again. Let me just say a few words about this event. Now, this event is a new platform that is organized by the Africa Division Scholars, Africa Division in IHR. It's called the Africa Scholars Meetings. So we have here, what we try to do is to have this platform that bridge between African scholars, those who are, scholars in Africa, and those who are also Africans but scholars overseas, to help, maybe connecting these scholars together, to collaborate together, to engage in some of the research, and also to get integrated with the IHR community. The speakers, coming with different backgrounds and, quite diverse in all aspects. This is not an event about qualifications. They're they vary from seniors to mid-careers to also young professionals. I hope everybody will enjoy this event. I would like to thank all the speakers who contributed to this event, and I also would like to thank some of the all the division Africa division members, but specifically those who have worked to help shortlist the speakers and make this events happening. Dr. Modipe and also Dr. Abu Rashid and also Cesar. Of course, without Elsa, as always in IHR, would be, nothing can happen. Now, before starting, I would like to, and before I forget, I would like also to let everybody here knows that we have the upcoming IHR Congress, which will be in Morocco, in Marrakesh. So the dates, please save the dates from 9 to 12 of December. Although this is the 6th IHR Congress, but it has not been organized in over 20 years now. So this is the QR code for the website. It's already open for registration and submission of abstract. Please do your best to join us. So here's today's speakers for the 6th of May. So we will start with an opening session with Professor Fatih Tahir and also with Professor Ali Homa. And then we will have 4 talks today by Professor Isaias, and also Dr. May and Professor Marwan Tmimi, and also Ms. Asma, who is a PhD candidate, but we are honored to have her here today with us. Now I think I'll just introduce the first speaker. I just stop sharing. Professor Fatih, you can start sharing your screen. I'll just give a brief introduction first. So, well, I'm honored to introduce Professor Fatih Al-Tahir. Professor Fatih is a chair professor of civil and environmental engineering at MIT. Professor Al-Tahir is a distinguished scholar in hydrology and climate change, and his work is highly recognized and published in top journals, including Nature. Professor Tahi is a recipient of several honorable awards, such as the Hydrologic Science Award of the American Geophysics Union in 2017. Professor Tahi's research focuses on understanding how global climate change, as well as regional land use change, land cover change may impact society through changes in patterns of water availability, extreme weather, and spread of vector-borne diseases. It is an honor to have him here today among us to inspire the African scholars in IHR community. Please, Professor Tahir, anytime you can start. You are muted, Professor, so maybe you could unmute and then, yeah. Sorry. So you are muted. I try to unmute you.
Okay.
Oh, there you go. There you go.
Okay. Thank you, Maurice, for the introduction, and thank you for the organizing committee for inviting me to participate with you in this event. It's really an honor for me to be with you here today. And I would like to talk to you about climate change, the main challenge facing global society and African society in the 21st century. And I would like to point to this picture that you see here. This is a picture of a nilometer. A nilometer is the device that's used to gauge the level of water in the Nile. And this is the Rhoda nilometer according to being drawn by David Roberts in 1850. And here, this pole here it has grading in it, and thus these two gentlemen, they come down and they measure the level of water. Another result, we have the longest record, geophysical record for any phenomena recorded by humans for any phenomenon for the level of water in the Nile. So Africa has been interested, Africans has been interested in studying their water environments for hundreds and thousands of years, if not more. So the challenge that we are facing today as a global society, this is the logo for climate change. This is the concentration of carbon dioxide over the Pacific Ocean, and it keeps rising. And I tell people, we could look the other way around, we could try and ignore it, but this is very stubborn. And so the chemical composition of the atmosphere is changing, and it's changing rapidly. And that's mainly, or it is due to human activity. This is the emissions. This is the emissions of carbon into the atmosphere. And you see here that it's not only that we are adding significant carbon to the atmosphere, emitting a lot of carbon, that rate by which we are adding is increasing. So in a way, it's a problem that's getting worse with time. And hopefully with society taking action, at some point we may see leveling and then declining in this chart. When you look at who is doing that contribution, different regions of the world have contributed to the problem. In Europe, in North America, and Middle East, and so on. Africa has been the least per capita in contributing to this problem. However, although Africa contributed very little, the continent is suffering from the impacts of climate change and is projected to even suffer more significantly in the future. This is the record of global warming, the changes in temperature during the 20th century. But the story does not stop here. It's not only temperature that's rising, but also water is being impacted. The hydro environments are being impacted. This is here the case for the Nile. In the Nile shared, the Eastern Nile shared by Ethiopia, Egypt, and Sudan. And in addition to the issue of climate change, we have that change happening in a background where the population is increasing and increasing significantly. And because of that increase in population, the share of water per capita is declining, bringing these countries into below the absolute water scarcity. So when we emphasize climate change is by no means the only problem facing the African continent. Population is another problem. But water and water availability is not the only issue that we are facing as a continent. When you look at diseases connected to water, like malaria, you see that Africa stands out compared to the rest of the world. Africa is clearly here the hottest spot for malaria compared to the rest of the world. Millions of cases every year, tens and maybe sometimes hundreds of millions, and death rates that are very high around the world. Most of them in the African, sub-Saharan Africa, and mostly with children, disproportionately impacting the poorest among these communities. So these are the two problems I would like to cover very quick. Water on the and in Africa, and how that relates to climate change. So some of the research in my group projected that climate change is likely to increase the supply of water by order of 10-15%. But unfortunately, that increase in the water, which is welcome news, is going to come up at the expense of increased interannual variability. What's shown here is basically the projections coming from the different models, the IPCC models. Each of these lines is one of the models for the different years, is showing that on average, more water, but on average, more variability. The water increases by 15%, the standard deviation increases by 50%, which is quite problematic. All of us who study hydro environments, they know that increased variability, the engineering solution for that is to build more storage. And this is a simple analysis here using the Hurst equation that shows that, with increasing variability, we move from the blue line to the red line, relating the amount of storage that you would achieve, or you would need to have a return period, basically return period for how much on average you get failures in your storage system. And because of the increase in variability, if you want to keep the same return period as current, which is about 60%, you may need to increase the storage by 50%. So this is a problem right on the domain of people who study hydro environments, which is how can we increase the storage capacity, not only in the Nile, but different regions of Africa to meet the need for storing water so that we could handle this increased variability. A very good example for where engineering solutions, where more hydro environmental studies are needed in order to address the challenges of climate change. Some of this in more details in a book that we published a few years ago that addresses this issue of climate change at the context of other challenges facing hydro environments in the Nile. Quickly, malaria in Africa, and here this is the case of malaria. In red is the rainfall over Niger, and these lines here, they show the cases of malaria in hospitals in Niamey, in Niger. Very interesting. When I first studied hydrology and studying water, if you show me two curves like this, I would say this is rainfall and this is runoff. And here you see how the hydro environment is connected strongly to the disease system. In this case, the disease is malaria, which is a significant challenge in the African continent. Of course, malaria is born in the hydro environment. These are water pools in a village, next to a village in Niger that my group studied, a village with the name Beni Zimbu. And you could see these here projections of conditions in terms of water levels in different parts of the village. And this is pictures of observations that had been carried at the same time. And so these water pools is where mosquitoes breed, and they go around, the Anopheles mosquito, they go around and transmit malaria. And so the origin of this disease, significant disease, is in the hydro environment. And there are questions about how changes in the climate system are going to impact that hydro environment, resulting in impacts on the disease, which is malaria. This is a schematic of how in my group we approach this problem. We think about it in like 3 pieces. There is a climate forcing that basically impact processes like infiltration, evaporation over land flow, dictated by parameters in the soil, the topography, the vegetation. That process, right at the heart of it, is study of the hydro environment, resulting in the formation of those water pools. The water pools then become the forcing for the entomology. And here we need to extend hands and collaborate with entomologists who study processes involving mosquitoes, like their flight, biting, overpositioning, development, and death. And that basically results in the number of mosquito bites that basically impact humans, interactions between the water environment and the human environment. And then that basically feeds back into the human system, the immunology, because as we know, for every disease, we have to have considerations for the immunity. You see from this picture, hydrologists, entomologists, and malaria doctors, they all need to be able to engage the study of this system in order to have satisfactory resolution of how climate change, for example, could impact the prevalence of diseases like this in Africa in the future. Some of these details are also provided in this book that's also available. There is links to it in my group. It shows one of my students here visiting a water pool in a village in Niger and studying, that environment to find out where the mosquitoes breed and so on. So in summary, I don't have much time, and I promised Moise I would stick to like only 10 minutes. In summary, to what the message I wanted to share with you is that projecting impacts of climate change on water cycle and related diseases in Africa at regional and local scales is a research priority for informing effective local adaptation. Africans will have to adapt, although they did not cause this problem of climate change, they will have to adapt to the impacts of climate change. And so that's a large area where many people, young people, could make careers helping African societies adapt effectively. Incorporating this local African context in terms of natural, economic, political, and social is not simply an issue of downscaling, from GCMs and global models to high resolution. It's critical to understand the local processes and the local risks from climate change. For example, when we looked at malaria, we concluded, for example, Niger is going to be different than Ethiopia. Niger, maybe malaria would decline as a result of climate change. Ethiopia, maybe malaria would rise as a result of climate change. We could not reach these conclusions without incorporating the local context, without going out in the field and understanding the conditions on the ground, and then bring that to the lab, bring that to our models, to our field work, and be able to understand things at the local context. Multidisciplinarity, as shown in the previous slide, multidisciplinarity is necessary. Multidisciplinary research on African hydro environments is needed, bridging the gap between these global projections and the local impacts, covering critical domains like water availability and disease transmission. Both of them are very important for society, and we have to handle them and research them carefully. And in doing so, provide very exciting opportunities for young people, for researchers, African researchers, to contribute, not doing only good research, inspiring research, but also research that's going to be helpful for their communities, for their local society, and for the global society at the same time. So with that, I conclude here. Thank you very much.
Thank you, Professor El-Fatih Tahir. That was a great talk. I know we are limited with time, but in case there is like a quick questions to Professor El-Fatih should be okay, especially from the panelist. If not, then I'll probably move to the, so feel free from the panelists if you'd like to speak right away. I'll just move ahead to other talks if you guys don't have any questions. I'll check the box. I think it should be okay.
Osman has a question.
Okay. Yeah, Osman Saidu. Osman.
Hi, thanks for the very interesting talk. Can you hear me?
Yes, I do.
Okay, so it's very interesting, but one thing which is missing is human behavior, economics, and politics. And most of us are focusing on physical impacts, but these are the driver of what's happening in the future of vulnerability. And so how far can we go with modeling given that these are so complicated to capture?
Yeah, I think that's an important question. As I alluded to briefly when I talked about the water in the Nile, it's a very complex issue. Even without climate change, there's a significant challenge in how to share the Nile water, how to help sustainable development, and that involves a lot of the social and political systems. And there are political issues related to that. There are social issues related to that. And so I brought up the issue of population. So we cannot assume that this is happening in vacuum. Even without climate change, the share of water is declining significantly because of population growth. When you look at malaria, as I alluded to earlier, we had to go to some of these villages and find out exactly the conditions on the ground, interact with the local population, and also the medical component of the research involves collecting data from the people living there. And so, so I totally agree with you that these problems are complex and they have many dimensions, and that's where I emphasize the multidisciplinarity. And multidisciplinarity is not only in the physical sciences, but also in the social and economical aspects of things. And so we have to be open to that. We have to welcome that. We have to encourage that. And that would be the way to make progress in this problem. So thank you for bringing that issue.
Thank you. Thank you, Professor Fatih, and thanks, Saidu, for this question. So I think there's some questions maybe in the Q&A, but because of the time, maybe we move ahead. Well, thank you again, Professor Fatih, for this talk, and thank you for joining us for this event. So I'm going to move ahead with our next speech for the opening today. Ali, you can start sharing your screen anytime. Professor Ali Erhoma is currently a senior project officer at Prima Foundation in Spain, responsible for Nexus Water, Energy, Food Ecosystem. He conducted comprehensive assessments of water, energy, food systems, and he is currently a worldwide renowned expert in Nexus policies and financing mechanisms in the Mediterranean region. He has extensive experience in working with diverse stakeholders, ranging from policymakers and researchers to local communities. He has more than 20 years of experience and led several research and innovation projects and published over 120 publications and several patents. It is an honor today to have him among us to excite our African scholars community about the importance of the Nexus and the funding opportunities in this field. Thank you, Ali. You may start anytime you want.
Good afternoon or good morning. It depends where you are. And thank you so much, Professor Muaz El-Wati, for your kind invitation So here I'm representing PRIMA. PRIMA stands for Partnership Research Innovation in the Mediterranean area. So today I will not go through the details, but maybe I would like to share with you what we are doing in the Mediterranean, because we are, part of all the regions. So we are open to Africa, open to any other region. And I think it will be a good opportunity to share with you where we are right now after, because we started in 2018, and now after 6 or 7 years in this program, we have very good, implemented project. But I would like to share with you right now where we are. So I put my screen, yes. So you can see that this program, as I said, it stands for Partnership Research Innovation in the Mediterranean area. It's, if I can say, a very a challenging partnership in the region, because why we are in this program? Because we are sharing a lot of, challenges and to address the challenges in the Mediterranean. And I think Professor El Fatih has already, displayed clearly the issue of the climate change. So the issue of the climate change, now we're experiencing the impact of the climate change. And even in the Mediterranean, we are, we have a lot of, insights regarding this issue. We are trying to address the climate change. The Mediterranean is one of the hotspots of the climate change in the region. And even, according to the last report of the IPCC, we will have more extreme event, hopefully not, but this is what has been, what has been reported in the last IPCC report. In the Mediterranean region, we will have a lot of extreme event, drought, and with floods, etc. So, to tackle all these challenges, of course, we need to work together, all the Mediterranean. We are 19 participating states, here 11 from the north and 8 from the south. And the secretariat is here in Spain. So I am basically right now in Spain, and we are steering this program since 2018. So the idea behind this program is to implement solution, not in the theory, but also to implement the solution on the ground. So we have right now, as you can see, the portfolio of our project. We have 238 projects. You see the number. It's quite high number of implemented the project in the Mediterranean with a budget of 352 million euro. And you can see here the participation from all the participating states, as well as from the private sector. So you hear the private sector, and in particular the SMEs, which are the backbone of the economy of the Mediterranean, are participating actively in this project, because we are thinking about the sustainability, and we are encouraging the participation of the private sector, in particular SMEs. So we have different thematic area. Water, you can see the number of the funded project per thematic area, whether in water, in farming system, in agro-food, but also in the nexus. The idea and the approach of the nexus in the region, I remember when I came here in 2018, we have only 3 thematic area, but we brought this idea because we believe, and I think since the conference of Bonn, since 2011, the nexus now is very important if we would like to go forward and to implement solutions and to tackle the adaptation or also the mitigation to climate change. So we cannot, address the climate change using, like, say, silo thinking. We are, using water or farming or agri-food. So the integrated management of the resources is the keystone, if I can say, for the adaptation and mitigation to climate change. So we have a lot of funded projects. You have the demonstration sites. Of course, we are open to the Africa region. So we are not only funding only the Mediterranean. If we can find a very good partner, an important partner in Africa, so if its participation is deemed essential, so I think we can fund this partner. So we are open to any contribution from African countries. But also another important point I would like to share with you, that we have a lot of success stories. We have a lot of implemented projects, in particular pilots and demonstration sites. So the idea now, we have this good practice and I would like to replicate the different case studies of the pilot in the region. So if you are interested in, for instance, in water project or also in the Nexus, we have a lot of success story. I would like to replicate what has been implemented in the Mediterranean region. Just to give you an overview on what has been funded so far, and starting from 18 to 23, and you see here the different priorities, because we have a strategic research innovation in the Mediterranean, and you can see here different priorities. So we are, as you can see here, we are funding a lot of projects in the sustainable integrated water management, and also on the water resource availability and quality within the catchment and aquifers. But also, of course, we have other projects in other priorities for the alternative water resources, irrigation, and etc. So you see here that the number of the water project we are, addressing the issue of the climate change directly or indirectly, whether in the thematic area of the water, but also in the thematic area of the Nexus. So just to give you an overview on the funded projects, and here it's another clustering based not only on the priorities, of our strategic research innovation agenda, but you can see here, and this is maybe you will not be surprised to see the irrigation and the water use efficiency is the highest number of projects funded so far. And I think this is evident and it's obvious because, with the climate change, with the evaporation, now we need to irrigate, because without irrigation, we cannot produce foods. And this is basically a very important challenge because first, we have an issue of the scarcity of water in the region. So if we will irrigate, we will use the blue water, whether it is from underground or the surface water. And this will create a lot of trade-offs in the region, because the fact to use the blue water, this will maybe create a lot of trade-offs between the different resources. Another important point regarding irrigation, because in the region, and for sure you know very well that in the water footprint, the main important part in this water footprint is the green one, the green water footprint, and the green, which is basically what we can find in the soil. So now we are a little bit neglecting the green water, and this is the major part for irrigation, because the water could be taken from the blue water, from the underground or the surface water, but also the water which is stored in the soil. And we need to take care with this water, because this is basically represents 80%, so for even more sometimes for some countries to produce foods. So you know that even for policies, sometimes they are giving a lot of incentives for the blue water for irrigation, but they forget to give the importance and to give incentives and policies for the green water, which is basically the most important one. So basically, this is the irrigation. I think it's very important, and now we are launching another call on how to tackle the question of the trade-offs and synergy between the different resources through the irrigation project. We have other projects also. I will not go through the details, but what's very important, we are funding a lot of projects that are producing decision support system. I believe the decision support system will be very useful for policymakers. We have more than 10 decision support systems that have been produced right now, and I think even if they were advanced in terms of technology readiness level. So of course, if you would like to have these solutions, I will be happy to share with them. Also, we are publishing all the booklets of the project in our website. And of course, it's my pleasure also if you would like to have any specific information regarding the results of the projects. In farming, what I would like to say here, because everything is linked, we cannot say that the farming is like in a sector, as I said, for the Nexus. In farming, we are more focused on the adaptation and mitigation to climate change. So basically, we are, as you know, there are three levels of the adaptation to climate change: the incremental adaptation, the adaptation of the system, and the transformative adaptation. In the Mediterranean, it's very difficult like that we are tackling the incremental adaptation with the basic one, the first, step towards the adaptation of the climate change is not sufficient facing the impact of the climate change. And now we are moving forward to have more project on the adaptation of the system or the transformative adaptation to the climate change. So we believe that now with the impact of the climate change, as I said, with the last report of the IPCC, we are giving more, attention to the adaptation of the system and the transformative adaptation to the climate change. So this is very important, and this, of course, it is well aligned with the Nexus approach. Here, you can see, and I already mentioned the different level of the adaptation to climate change. We have more projects on the adaptation of the system. As I said, this is linked to the green water footprint, because when we are dealing about the adaptation of the system, so and more of our food products are generated or produced by rainfed agriculture. When I said rainfed agriculture, it's more the green water footprint. And here, to save and to avoid, to lose to the evaporation, because now we are experiencing the issue of the climate change, we need to encourage the agricultural practices in the region. And we have a lot of projects. The highest number of the projects are targeting the adaptation of the climate change through the implementation of the agricultural practices. But also we have other adaptation, like the incremental, like the varieties, for instance, the resistance or tolerance of the varieties to biotic or abiotic stresses, and other, incremental adaptation, which are good but are not sufficient in front of the impact and the of climate change. Here, I would like to highlight an important issue here for the farming system. We are targeting the smart farming system. The smart farming system, most of our food production in the region, and I believe also in Africa, are produced by the small farms. And the small farms are always used the rainfed irrigation. So basically, the agricultural practices is well fitting in this in this scope, and that's why we are encouraging a lot of practices that are sustainable and they are smart to the climate change. And by the way, there is a new partnership on the agroecology. They just started last January, and another partnership dedicated only to the agroecology. Just I will end up here for the farming, for the transformative adaptation. And now we are encouraging more a lot on the agroforestry system. And I believe agroforestry is very, very useful for Africa. And now the European Commission, they are funding a lot of projects with EU Africa on agroforestry. Agroforestry is another kind of transformative adaptation to climate change. And I believe for African countries, it's very, very useful for the adaptation to the climate change. The agri-food, just to give you an overview of the agri-food projects, we are more, on the food safety and the also on the implementation of the innovation in the agri-food. Here, I would like to come back to the presentation of Professor El-Fatih, and he said that for the health issue, this is very important, the component of the health, because it's linked to the foods, it's linked to the agricultural practices, and even now it can also highlight the component health as the component number 5 of the Nexus, because we have the water, energy, food ecosystem, but the health is the component number 5 of the Nexus, and we would like to give it more importance for the next period, because always we are maybe targeting the resources, but the health is not considered as an important component. Here you can see the project distribution of the projects according to different thematic areas, but you can see in particular we are more focused on the innovation and also on the food safety when it comes to the traceability and the authenticity of the agri-food products. Just maybe to end up here and to share you some important innovations. So here you can see all the innovation solution that we have implemented, that we are implementing in the Mediterranean region. Once again, the innovation solution will be useful for you if you like to replicate, but also if you like to participate in our program. We have very good news that the program has been extended by the European Commission. So we will be launching for several courses in water, in farming, in agri-food, or also in the Nexus. If you'd like to participate, of course, you are more than welcome. I would like to stop here for the sake of time, and thank you so much for your attention. And back to you, Professor Moaz.
Well, thank you, Professor Larry Homa. This was a wonderful presentation. You know, we can have an overview of what Prima has been doing. The time is pressing, but there's one question, because this is the main purpose, Ali, you are here. The question is, if a project support, does the project can be extended to East Africa? And I think you mentioned a little bit, but perhaps you can echo, the answer to everybody here focusing on this, because we would like to encourage as much as possible African scholars to feel, have the excitement to really go ahead and apply for Prima course. Yeah, please, Ali.
Yes, exactly. I fully agree with you. Sometimes people, they are asking us, you are closed in the Mediterranean like the 19 Pacific. No, we are open. So we are giving funds to any country, even in the US, in Switzerland. So we have Palestine. Also, we funded the research team from Palestine, from Africa. Because here, if your role is very important in the project, I think you are eligible. We are not completely closed. No, we are in the Mediterranean. We are open to any contribution from African countries. And also, if you like to replicate, in case you would like to replicate what has been implemented, of course, we are open to share with you our best practices. And of course, if you like even to participate in Horizon Europe or EU Africa, so you can maybe try to make use of what has been funded by our program.
Yeah. Okay. Thanks, Professor Ali Homa. I think that was quite, I would assume this was quite clear, and I really want to encourage all our fellow African scholars to, be encouraged and, go ahead. And if you have cool ideas, as you mentioned, is more implementation, please go ahead and apply. Well, thank you, Ali. I apologize for some of the attendees. They have some questions that maybe we don't have to answer. Feel free to email the speakers. Now, I would like to move to the, to more of the research talks that, from the speakers today. So I'm gonna just go ahead and start with the first speaker. First of all, I want to make sure Esais is over here, because our first speaker is Esais is not here, right? I just apologize. Just a moment. Want to make sure. Okay, so if Esais is not here yet connected, maybe I'll just, if it's possible. Yeah,
I might volunteer. This is Marwan Tamima. I might volunteer to take that
to start first. Oh, Marwan,
if
please. Yeah, because Esais has mentioned to me as a problem to connect, but maybe.
I'd
Yeah,
be happy
Marwan,
to jump
please,
on.
I can start with you first. I'll just give you a quick introduction, and then you can start sharing
Thank
your
you.
screen anytime. Well, Professor Marwan Tamimi is Associate Professor in Civil, Environmental, and Ocean Engineering Department at Stevens Institute of Technology in New Jersey, USA. Professor Tamimi obtained his PhD degree in water resources and remote sensing, and his MSc degree in hydrology from the University of Quebec, Montreal. So Professor Tamimi holds over 15 years of extensive experience in industry as well as in academia. Today, his talk is leveraging remote sensing data and advanced numerical models to enhance the modeling of river discharge. Professor Tamimi, anytime, please, you may start. Thank you.
Thank you so much for the invitation, and thank you for accommodating again. I'm very happy to be part of this call. So I hope you can see my screen just to confirm with the first slide.
Yes, yes.
Excellent. So, so at Stevens Institute of Technology, our laboratory, the iSmart Lab, has 4 pillars that we are actively developing. The first one is the use of satellite imagery and remote sensing which is also very useful in Africa, where data in situ, on-the-ground data are scarce. The second pillar covers the use of and the development of ground-based observations. This is another area also that we would be happy to work with scholars in Africa to extend. I will go and cover a few slides later, cover this part with a few slides regarding the development of low-cost sensors that are suitable for remote areas in Africa. The fourth one is on the use of machine learning. It's a must nowadays, as machine learning is supporting greatly the development of models and modeling capabilities. And the last one is the use of numerical models, H&H model, hydraulic and hydrologic model, to support the forecast of stream flow. So those four pillars altogether, we are working on developing them, the research, the fundamental research, as well as the applied one, to enhance the forecast of stream flow, across scales, local, regional, and continental as well. So we are, as a side note, we are part of a cooperative institute that is funded by NOAA. NOAA is a federal agency in the US that has a mandate to operationally predict stream flow. And NOAA, through its office, the National Weather Service, is working on operationally predict stream flow. We are among one of our members among many, about 20 universities in the US, founding members of this cooperative institute that is called Cairo, that happens to be a city in Africa. And it is largely funded at the level of 360 million by NOAA to advance research and forecast in hydrology and hydraulic. Because of that, we think that it has never been a better time to work on hydraulic and hydrology in the US because of these opportunities. So in the US, we, through NOAA and through this cooperative institute, we work on the enhancement of a national water model. It's a nationwide, seamless hydrologic and hydraulic model. Additionally, it also covers the coastal processes and couples them with hydraulic and hydrologic models. So the model is gridded with routing schemes in channels and force it with different meteorological forcing. It issues 4 types of forecast: the hourly one, the short range, the mid range, and the long range. And each one of them is using a certain type of meteorological forecast. The short range one is updated hourly. The mid range one is up to 2 days, 4 times a day. It means the meteorological cycle, the forcing, the precipitation, and meteorology, the rest of the meteorology is updated every 6 hours. And the long range is up to 30 days. Of course, I mean, the short and the mid-range are very useful for a flood and flash flood forecast. The mid-range are very also suitable for irrigation and also water resources planning. This is also to say that this model is open source. We also worked on testing this model in sites in Africa, in East Africa mostly, and other regions. So all the model, the development tools, all the post-processing, pre-processing tools are all open source, and we are happy to provide you with assistance to those tools. The model uses gridded when it comes to the overland flow. It uses a gridded scheme based on what we call the NOAA-NP model. And then as per the overland flow itself, it uses the diffusive wave, and then water from the overland flow gets into the channels. And there we also have the use of the Muskingum or the diffusive wave equations to do the routing in the channel. We are working on using remote sensing to adjust the routing scheme and improve the flow from satellite. For instance, we are using the satellite data to update the roughness in the channel and the floodplain. So very quickly, we have contributed to the estimation of soil moisture, always in the optic of improving the stream flow forecast by assimilating it in graded hydrological models. We use satellite data from a mission called SMAP. It's a NASA mission that we contributed to its CalVal activities, calibration and validation. This is an example in upstate New York. Our student worked with NASA scientists. This is Mohammed Abdelkader, one of our PhD students, a scholar who was born and raised in Africa and making great success in the US. Just came back from Alaska assisting tribes and locals in Alaska with satellite remote sensing of ice and snow. We also work with the DEP, the Department of Environmental Protection in New York City. The division is responsible for supplying water, fresh water to New York City. It's about 10 million people. Water comes from upstate New York. In the Catskill comes elevated in reservoirs in upstate New York, and then there are tunnels dug in the bedrock, bringing that fresh water to New York City that is at the coastal level here. And these are tunnels, they are about 140 kilometers long. This is probably among the longest man-made tunnels in the world. And our role is to improve the forecast of stream flow to support actually through this grant funded by NASA, support DEP in New York City to predict the stream flow, especially during cold regions due to snow and ice presence, and the inflow to their reservoirs. We developed a Google Earth Engine platform for them to look at the amount of snow that is accumulated, compare, and then convert it into stream flow and then influx to their reservoirs so they can decide how they manage their reservoirs accordingly. We also use satellite data to look in the Hudson here. It gets really cold in the US, in eastern US at least. And then that's ice that forms on the Hudson right along New York City, Manhattan. And from satellite, we can look at the displacement of ice with two overpasses from satellite, and then estimate the surface velocity, and then use that to validate our Stevens Flood Advisory System, which is a numerical model that is operationally used in the region to predict flooding, coastal and inland flooding. Mohammed and the rest of the team worked on incorporating citizen science data. It is something that we really would like to develop also with partners in Africa. We use open source tools, Google Earth Engine, again, and we integrate data from crowdsourced data from citizens, basically. There are different platforms to share those data. Some of them is the NASA Globe open source application that is available to all, and globally citizens, they update or upload inputs about environmental variables. And we have scripts to fetch those data and post them in Google Earth Engine. So these are capabilities that are all open source, and happy to collaborate with Africa-based partners to develop them and expand them. As I said earlier, we also invested in developing low-cost sensors, from rain gauges to surface velocity to soil moisture, etc. We developed at water level for flood inundation or rivers. A sensor like that one would cost about $300, fully operational, and it uses radio frequency, low energy network. It doesn't require Wi-Fi or cellular coverage unless you need a gateway, but within the network, you can use all the sensors together. We deployed those sensors in Hoboken and expanding the network in New Jersey. But again, these are low-cost sensors. Everything is open source. and the parts are available over the counter, let's say. So this would be very useful to expand the capabilities to monitor stream flow in Africa, Western region in Africa or Eastern as well, and enhance the capability to monitor stream flow. These are examples of the deployments that we have done and the capability to measure stream flow. And we developed portals to in real time check the variability of flood water, inundation, and also rainfall with an open source interface, web interface. I moved to the modeling. We developed models across scales, as I mentioned, for water level and stream flow forecast. This is where Stevens is in Hoboken, New Jersey. Manhattan is on the other side, and our university here. Hoboken is a flat, flood-prone area, and we developed numerical models to look at flood inundation. And also, in addition to flood inundation, something that we are also interested in looking at is velocity. Flood risk is really related, in addition to water level, is really related to the momentum of flow and velocity. So that's why we are working on enhancing the capability of hydrological models and hydraulic ones to get velocity correctly as well. This is two events, extreme events, Irene in 2011 and Ida recently in 2021 that caused a lot of damages in our area. So we, as I said, we look at this across scales, the local and the regional scale. This is zoom in when it comes to the velocity. That's a major train and bus terminal in Hoboken to New York City across on the Hudson, on the other side of the Hudson. Expanding on the scale, we look at the larger, like the DEP, now the Hudson. At the mid scale, let's say this is the Hackensack River. It's in the New York City metropolitan area. It uses a model called WRF Hydro. The model WRF Hydro is the engine of the National Water Model currently, although the National Water Model is developing new schemes and new capabilities, but WRF Hydro is an open source model, again, that is available online. It runs on a Linux platform, and we use this model to run it at again 50-meter resolution instead of the native 1 kilometer to 150-meter resolution. We are running it at 50-meter resolution at block scale to predict urban flooding with it. And then we used again citizen science data, as we did in the case of in Alaska with Mohammed, to validate and calibrate the model. These are again examples from crowdsourced information that we fetched from social media data. We used AI again to understand the operation rules of reservoirs. A lot of dams and reservoirs here are managed by companies. The decision rules of and the release and the storage of water are not necessarily available to public. And that's why we use machine learning to try to understand the operation rules and then use that to integrate them into hydrological models. In addition, we use high resolution radar data to look at rainfall and estimate their return period. We, in addition to the different ranges of forecast, the short range, the mid range, and the long range, we also developed what we call the nowcasting. It's in the horizon of a couple of hours, 2-3 hours ahead. And this is very, very important for disaster management and disaster planning. Again, these are examples of nowcasting tools that we developed. I would end with some conclusions and opportunities. First, I would like to stress the fact that remote sensing and in situ observation, they go hand in hand to support numerical models in their role to predict stream flow and hydraulic variables across scales. So definitely there is a need, especially in Africa, to leverage these capabilities and look at options like using the low-cost sensors In addition to that, there are new missions. We can mention the NASA SWOT mission that was recently launched, and data was released as a pre-validated version in December 2023. Data are available to measure stream flow globally, in Africa, of course, included. There is a NISAR mission. It's a joint mission between NASA and India for soil moisture. Among other, it uses a radar. All these data are freely available. They are also will be available on the cloud, so we don't need really data storage capability, as long as you can get the data through the cloud. With all this said, I would like to mention that we have openings for PhD positions as well as postdoctoral researchers in the field of water resources, always at Stevens, especially through our role part of Cairo. And we would be happy to see scholars from Africa shine in the US, and then feeding back to Africa with the expertise in this field. Thank you for your attention.
Thank you. Thank you, Professor Marwan Tamimi, for this great talk and a nice overview about your research. So I would like to check if there are any questions from the panelists or from the attendees. You may feel free to write some of the questions, maybe the attendees or the panelists may speak right away without, you know, no need to raise your hands or anything. Just feel free to discuss or have any questions. So maybe if no questions, I can just, Marwan mentioned one thing. When you mentioned there are, these are, I mean, this is not in my field, you know, this remote sensing and everything. But I was wondering, when you say they are open access and you have used them for Africa regions and everything, how would you say, you know, how easily or accessible are they for people who doesn't know, you know, this, you know, these online platforms? Are they challenging? Because, you know, when one may wonder that we may organize some sort of a training that this like scholars or maybe a young professional may require a certain training to really get used to these, you know, open source platforms.
Well, I mean, I take the example of the Google Earth Engine platform. It is really well documented, well supported, and I believe that is relatively easy to get into it. I mean, and Google Earth Engine hosts a lot of satellite data in it, so you have free access almost to a lot of, I mean, almost all satellite data and model forecast as well through Google Earth Engine. The tool is really very well documented. You really don't have to know a lot of coding. It's very, it has like very basic Java, I would say, platform, and there are a lot of open source scripts that you could use.
I see. Thanks. Just some questions came quickly. So just one thing, I think they wanted to mention whether this WRF model is open source for East Africa as well or not. I think
yes, it is open source. Yes, the model is open source. You download it and you customize it to East Africa or any other watershed in Africa, whether small or large watershed.
Okay, so this is an interesting question. Just say, can the remote sensing be used in detecting leakage in pipeline, and how easy can be applied in a remote area in parts of Africa? Has ever been being myself in this field of leak detection pipeline? Actually, that's a good question. Just wonder, have you ever used this remote sensing for pipeline like leakages? I mean, you have a
well, I had the chance to work in the Middle East with oil and gas companies when I was there, collaborate with them, and we used high resolution satellite data to look at leakage from oil pipes. Basically, some of these oil terminals, they transfer oil, crude oil from the terminal or the wells to the terminal, and under the weight and the land subsidence, some of those pipes, they leak. So we use hyper resolution satellite data to detect those leaks in the desert in the Middle East.
I see. Thanks. Well, I think there may be some other questions, but I'm sorry we have to move. But feel free to contact Professor Tamimi anytime. Well, Professor Marwan Tamimi, thank you so much for
My
your
pleasure.
for
Pleasure.
your
Thank you for the
presentation.
invitation. I
So
put my email. I can put my email in the chat, and I'm happy to answer.
please, and let them contact you. Some of them mentioning
Sure.
they're looking for opportunity, of course.
Sure. Thank
Okay,
you.
so I think we're going to move to our next speaker. Sais is now here with us. Professor Sais, please feel free to start sharing your. Sorry, I'm muted. Okay, I'm mute myself. So Sais, just share your screen. Just a brief introduction. So Professor Isai, full professor, senior researcher and practicing engineer at Jimma University in the field of water and in the field of water and in the field of water and hydraulic engineering. So furthermore, Professor Sais is a visionary leader who firmly believes in transparent shared governance and who fully embraces culture diversity. So Professor Sais, thank you for being here. I think today's talk is nonlinear problem solving water technology and achieving efficient water management, challenges and opportunities. Please, Sais, anytime you may start.
Yeah. Thank you so much, Professor Moise. Can you hear me now?
Yes, I can hear you very well.
Thank you so much. Sorry, but I was attended as a participant, but I didn't miss all those interesting 3 presentations. So welcome everyone. And this is a topic already mentioned by Professor Moise. So the topic is a little bit, it looks general. I did deliberately this topic because this is African Scholar events. So we need to see and share the overview, some important point with regard to water management aspects. Okay, so as a topic indicate, I'll talk a little bit of some challenge and opportunities in my research groups with regard to water management. And then I will show you some specific research areas that's going on in my research group. Well, first, just let's try to diagnose the globe where we live and what type of research are also needed, particularly as a continent in Africa. So when you look at this, already mentioned by Professor Fatih and as a presenter, there are a lot of challenge that what we have in Africa. One important thing is population. It's now 8.1 billion, as you know. Africa is the second most populous continent in the world. In 2050, it will be reached 2.5 billion people. That's very important to think. This is also accompanied by urbanization. The urban growth is very fast in developing country. You know, each developing cities, most of them, they received about 5 million urban residents every month. This is the point what we are working as a researcher, which also, again, accompanied by industrialization. In our continent, as Africa is very rich with different natural resources. A lot of industries are coming as advantages, but there are also a lot of disadvantages when we talk about natural resources. But industrialization is also important. To make things worse, we have a conflict, you know that in global, you can just pick like Ukraine and Russia, you can pick Israel and Gaza internally in a continent in Africa. You know, being as a researcher, we have to know in which situations are talking, especially as an Africa, and mainly as developing countries. This is also very important. Particularly in Africa, we do have also a series of infectious diseases in all over Africa. There are a number of, we call it, deadliest infectious diseases are happening here and there. Again, the most important thing is already mentioned by previous presenter, the issue of climate change. Okay, so when you look at all these situations, now the point is, as a globe, already the carrying capacity of the ecosystem was exhausted. That's true. The current researcher, future researchers, this is a place, this is a platform that we need to work. And we have to think a little bit of out of the box. If you go the same business as usual, you may not reach and solve the important problems that what we have. So this indicates, in general, we are running out of resource. Among the different natural resources, as you already know, water resource is the most precious resource and indispensable natural resource. If you look at to bring sustainable development, we can't neglect the water resource. But now the point is, are we really looking properly at the water resource, what we have? And what's our thinking about water resource? Are we really considering only the blue water that is accessible in our continent or in our city? If that is the case, nowadays it's very hard to reach the sustainable kinds of development. So the climate change, the urban populations, industrialization, and the conflict, disease poses a continuous challenge to water resource management and service delivery. Remember, this is very important. Okay, now let's bring you to the water resource. Simple question. Do we have shortage of water resource? What do you think? Do we have really shortage? Well, the answer is simple. If you look at global context, the answer is no. Because 1% of Earth is water. 3/4, 71% of the waters make up the Earth's surface. What does it mean? Is there a shortage of water resource or scarcity of a technology to convert this useful infinite water resource to freshwater resources? Is a good question. So now, if there is 71% of the Earth's surface, now the second question may be quickly, where is Earth's water? Again, the answer is very simple. We know that 97% goes saline water in ocean and the sea. So this current researcher, future researcher, are we going to consider this non-conventional water resource as a useful water resource? It's a very important question. Let me take you from the globe to our continent, Africa. How is Africa a water resource? Africa is surrounded by water, isn't it? If you look at here, there's Atlantic Ocean to the west, to the East Indian Ocean, here both, to the top, to the north, if you look at Mediterranean Sea and the seas, kind of the Red Sea. And we consider this important, plentiful, useful water resource as an important water resource to our continent, to our country, is a big question. Now you bring the technologies to use such infinite water resource. Very simple technology is desalination technology that converts saline water into freshwater resource. Quickly, let me show you again as an overview of the issue of desalination technology. This part is one of the important parts of what we are working. Currently, there are two important desalination technology. As you know, the dominant one was multi-stage filtration technology, and which is really very important, but brings some byproducts and some problem in the environment with regard to concentrated brine solution. I mean, pollutions and also little bits of carbon dioxide emissions coming from this conventional desalination technology. Now it's changed into RO. The RO is very important, but still, cost-wise, is really cheap compared to MSF. But still, we need to work a little bit to reduce the cost and to make more efficient. In this regard, let's think the African continent, the infinite water resource. Do you know how many countries are coastal country in Africa? 70%. 38 country out of 54 is a coastal countries. Are we consider the infinite water that's surrounding for us? Is a big question. As a research indicates, insignificant really. We are not making better with regard to the infinite water resource. So in this regard, we have been working in my research team, we call it the HAD technology. The HAD is very simple abbreviation, which is a bit different from the hydro environment part. That's what we have seen from the previous speaker. HAD is hybrid adsorptive desalination. This is just to use different types of the soil that what we have in our continent and the rocks and come up with, you see, the different green adsorbent. These are different indigenous with a little bit modified kinds of adsorptive technology. We use this adsorbent through batch and column and experiment. We have done several researches, accumulated experience. It is advancement of technology. And the cost is now in Arrow already is very less compared to conventional treatment. The conventional water treatment is reached up to $3 per cubic meter, but Arrow is already make $1 in general. This even makes less than that is about 0.5 cents dollar per cubic meters. That makes a difference when you talk about the water resource in Africa. So there are many researches conducted. As an example, if you look at these two publications since 2009, we have been doing a lot with adsorptive desalination technology. You see, this is the one, just as an example, cationic removal. You know, cadmium is a very serious problem that to remove cadmium from the waters, and chromium is an ionic part. This is also a serious problem. We have a lot of these toxic heavy metals in many parts of developing country, but also developed country. We can really remove with advanced technology, but because of finance infrastructure, we cannot go with those advances. So we need to look at a solution for African problem, African solution about it. So this is one important thing that we are working currently, still going on as a pilot scale, and we are moving forward. But the most important, again, okay, let's say we have a lot of infinite water resource, but how about the finite water resource, the fresh water resource? I'll show you very briefly, quickly, the African continent. We have surface water. Yes. We have about 63 transboundary river basins, which cover, you see, 64% of the continent, especially sub-Saharan Africa. That's a lot. If you look at also the most important, the largest river as an example, the Nile, the longest river in the world that we have in Africa, isn't it? The Congo River, the second largest world basins in the world with regard to the areas, with regard to the drainage. That's also very huge. And also, if you look at the fresh lake, the 3 of the 10 largest fresh lake on the earth, like Lake Victoria, Lake Tanganyika, Lake Malawi, are exist in Africa. So Africa, with regard to surface water, freshwater resource, is really blessed very well. Now let me take you, because this overview is very important, to think a little bit differently when you talk about water research. When you come to the groundwater, recently, a British Geological Survey and University College of London conducted and come up with this map. You see groundwater, what we have? The deep blue is more than 20 liters per second, you can imagine. Especially if you look at here in the North African part and some parts of in the middle. Very huge in amount. Those researchers, you see, they came up with such conclusion. They urged that the total volume of water in aquifer underground is 100 times the amount found on the surface. What does it mean? That's a lot, isn't it? If you look at Nubian sandstone aquifer, which is shared by Libya, Egypt, Chad, and Sudan, trillion and trillion fresh groundwater resources exist in that particular area. I can give you one example that's recently conducted. It's only if you look at Egypt, more than 115 trillion cubic meters of high quality fresh groundwater resources exist. But the question is, this is really shocking always, why Africa faces considerable water crisis. We have seen all the infinite water resource, the finite water resource is really pleased, but still the problems are exist. So that's why now the current research, especially in my area, how brings sustainable kinds of technology that really increase the water supply system and reducing also the demand, the consumption in our continent. Okay, now why this is happening? One of the issues is mismanagement. This is really true. This is, you don't need to conduct even research. Just go have a look what we are going to do in at home levels, at simple village level, the water management aspect. You know, in Africa, we use such kind of system, isn't it? We supply the water and bring all things as a wastewater, the combined system. Remember, it's not only the water coming to the institution, but all the rainfall with regard to infiltration in flows is considered as a wastewaters. We have a very poor distribution system that's difficult even to detect as a practicals. So recently, the World Bank has come up with such kinds of data also. Frequent network breakdown. And account sources is very, you know, the water loss is reached 35 to 40%. If you look at this, only the real loss, 16.1 billion cubic meters per year. You know what it means? Which can enough to serve 200 million people. That is a lot, isn't it? Many small African countries, 20, 25 countries, can be adequately getting the water if we try to manage. I'm sure Professor Moise can talk a lot about the hydraulics, the distribution part. There is a serious problem what we have. One research, they conducted the issue of mismanagement and interruptions of this water delivery. The two professors from Egypt also indicated that if the Egyptian distribution system is maintained properly, they can save 40 billion cubic meters of water. Can you imagine how huge an amount? We are not also immune. If you come to Ethiopia, there's huge amounts of water loss. That's a serious problem. So this is the area that we need to work. I'm sure Professor Moise and other colleagues can help a lot. But recently in Addis, we are working with digital twinning technology for 10 million people and agrees with some of the Dutch companies to maintain early detection in the distribution system and working a lot with this distribution system. That can a little bit mitigate the problem. So that is the mismanagement aspect. But not only this, what about the issue of wastewater? You see, this is out of sight, out of mind thinking. Everything, you just use it and then consider as wastewater. Can we really work in 21st century and considering this is just wastewater? Never use that, never. In the globe, you know, this is the data in 2020, studied by a Canadian university, about 380 billion cubic meters of wastewater are produced annually worldwide. Huge in amount. And this research indicates in 2050, 51% increment. You can calculate how huge in amount. Should we neglect this wastewater as it is? What is really wastewater? We always talk about 99.6% is water by volume. So the system what we have in conventional wastewater treatment, advanced wastewater treatment, they are all what we have in many developing countries, including my continent, is linear problem solving. In a linear problem solving, you treat, you remove some of the solids, some of the things, and then, but finally, the effluent still contaminates the environment. You see, the effluent comes whether conventional, whether advanced, whether some of them even not treated that way, contain very serious pollutants, which really stay in our environment, like pharmaceuticals, dyes, heavy metals. You're not surprised because the surface water especially contain almost everything. Why? Because the linear problem-solving approach, the effluent that comes from treatment, or those wastewater never treated and polluting the water body. Whatsoever technology if we have, it's very hard to work with the polluted waters unless you bring back to the freshwater system. So this is an important area, again, what we are working in my research team. Recently, we just evaluated the water pollution, especially surface water. We did a pharmaceutical in freshwater, the Europe and the African continent. This is very interesting, by the way, highly cited publication, the articles. You know, about 4,000 times the pharmaceuticals exist in Africa compared to Europe. 4,000 times. The type is a lot. Well, there is also a problem in Europe, but in Africa it's highly concentrated. Why? Because, you know, pharmaceutical is just like this. See this picture? Yeah, it cannot metabolize. Many of them, just adding in the wastewater or taking as a drug medication is all the same. You'll find in the freshwater. So that's what we take. The second one, what we have seen, the industries, what we have in many developing countries is agro-industries, is water consuming. I can give you one example, the coffee, because Ethiopia is one of the top coffee producing country in Africa. You know, to produce, do you like coffee to drink? Look at 1 cup, consume 140 liters. As an engineer, can you work by designing, redesigning the process to minimize the water? Where it goes after a cup of this, it's huge in amount, isn't it? So those all things comes and brings a serious problem in the surface water, what we have. So to tackle this one, we have been working now with a non-linear problem-solving approach. What does it mean? The linear problem-solving is an approach, especially with regard to water resource. We need to consider all forms of water as a useful water resource. That's an important message. All forms of water. If you look at wastewater, wastewater is a very rich resources, can be reused or recycled. It's not only to bring back the fresh water, but you can use for energy, you can use for organic fertilizer. A lot of these 2 parts today. Just if you look at this one, it's huge in amounts. There are many countries utilize this circular economy approach and taking the non-conventional water resource and bring back to the system. So with this regard, we have been doing a lot. That's a technology, we call it AOP, Advanced Oxidation Process. Very simple. You just take anything that comes out here and bring back to the system. How? It's not as it is, because this is dangerous to some extent. It should be treated, recycling back to the system. So the treatment technology, which is a 21st century technology, we call it advanced oxidation process. There are 2 types of technology, homogeneous and heterogeneous. These are the technology what we design now. With regard to homogeneous, we just start simple photophantom. I'll not complicate things because some of you may be far from this, but in general, is producing the very strong oxidant, we call it hydroxy radical. And we have been working a lot with homogeneous. Heterogeneous, differently, because you have 2 important advantages as an African. One, we have a lot of mineral, natural mineral. You see like titanium dioxide and nickel ferrite, graphenes, a lot of them. Second, we have huge amounts of sun, isn't it? The sunlight. Ethiopia's 30 months of sunshine. That's a lot of energy. Using this, we can produce a lot. Some of the important advantage of this advanced oxidation process already communicated. I can show you. These are the heterogeneous, which is published again with a high impact journal. You can feel free to have these papers. You can have a look here. We use just graphene and simple kinds of nickel ferrite, nanocomposite, and it's very effective to remove different persistent organic pollutant. The other one is, this is a homogeneous one, again, published with high impact journal, and this is also very effective to utilize. So now, in the interest of time, just to summarize what I try to talk about, nonlinear problem solving works a lot to manage the very precious resource what we have, the water resource, in an efficient way. So as an outlook, our research experience is there's 3 important things, but keep in your mind, especially the young African scholar, whatsoever research you do, first you need to know your platform. Overpopulation, the urbanization, industrialization, the disease what we have, the climate change, and the conflict. Within this situation, yes, we can. We can work. In the context, in African context, we can solve the problem. So one of our research experience is hybrid advanced desalination technology. You are welcome to join my research team. The second important is in advanced oxidation process, both the heterogeneous, homogeneous, you are welcome. But research itself is not really enough in my view, because I came from the university. The education part is also very important, because when I ask always why Africa face considerable water crisis, it is a capability, it is a capacity to exploit, to manage the resource what we have. So the curriculum, our education system should be in line with the problem what we have in our context. With this, definitely we have plenty of water resource. Even with the face of climate change, we can bring sustainable water management. Together, if we cooperate, I'm sure we'll be one of important, not simple research, not only publication. We go beyond with that. That's all what I have, Professor Moise. Thank you very much. And I'm okay for any question. Thank you.
Thank you, Professor Isais. That was a very nice talk. I can, there was so many things coming up, from all directions on all water problems that you mentioned. I would like to welcome anybody from the attendee or panelists to have, a question. Please go ahead, and I'm looking at Q&A if people are still interacting with Professor Tamimi, but okay. So I would like just some of them maybe take time to write questions. You took a little bit over time, but just have a quick question. I was really interested to see you talking about the coffee. That was, it took my mind. I was wondering, because all, especially in North Africa, was also a huge consumers of coffee. I wonder, how do you make the assessment? How would you know how much consumptions of coffee, or how do you make the assessment, like how much water has been consumed for a cup of coffee? Is there any like specific how accurate, basically? I'm just wondering. I don't know. Is Isais, I think is you are muted. I think if you are talking, I think you're muted.
Yeah, thank you so much, Professor Moise. Well, in general, it's not only coffee, but if you look at the industries what we have in Africa, many of them are water consuming. A lot of them. If you like to produce 100 metric ton of paper, currently we are using 100 metric ton of water for 1 metric ton, paper, which means 99 metric tons of water is considered as a wastewater. When you come to the coffee, this is, by the way, literature-based, and we came our calculations also. In the wet processing, if you look at only the wet processing to clean the water and remove those husks and mucilage and bring to the market, huge amounts of waters are consumed. If you go with the dry processing, that can save a lot, but the quality of coffee will be reduced. So usually encouraged to go with the wet processings. We just calculate in hundreds, like 1 quintals of coffee, how much water, that is very rough. That's how much water can be consumed only for wet processing technique. So significant amounts of water can be consumed. But 1 cup for 140 liters, I was also very surprised and have a look. So the overall footprints with the product part, they calculate and come up how much of waters is taken to come up with 1 cup of the coffee. So they consider only the production part, the processing part, and the finals, cleanings part also. That's why they came up with this. But it's really huge and huge in them. Thank you.
I see. I see. Quite interesting. Thanks, Professor Sais. Saidu, are you raising your hand? Would you like to speak?
Yes, thanks for the very interesting presentation. So you have shown that we don't have water resources quantity problem. And you have shown that there is almost a technology to solve every problem you have. But the issue is, can we afford the technologies? You can have a farmer who's living on top of the biggest groundwater resources, but don't have the means to buy a pump and use it for irrigation. So sometimes I think it's not about technology, it's about being able to afford the technology.
Yes, that's completely agree with Saidu. What I would like to mention here, one, we shouldn't neglect the different water resource what we have in the continent that I try to bring to the audience as a young researcher also. But the second one, yes, let's work with the water technology and make more affordable. How can we make affordable? If we try to do some of the technology, not simply importing, but as an Africa, if we start a simple startup and scale up those technology with available, energy is also very important. Nearly 60% of the cost of this water technology goes to the energy. If energy is locally available, the technologies, for example, if you look at this HAT, they are all locally available. Using those local available material, that can reduce the cost and makes better affordable for the poor community. Is that easy? Not really. That's why we are working a lot, but I'm sure we can make it in the future. Thank you.
Thanks. Thank you, Sais, and thanks, Saidu, for the question. So I think, given the time, I mean, we're sorry we're running a bit late, but I think it's okay. Professor Sais, thank you so much for your presentation.
Thank you.
Thanks for your contribution. Okay, so Dr. May, maybe a brief introduction to our next speaker. Dr. May Sool is an environmental engineer specializing in the interactions between water security, climate, and health systems, including the application of total systems thinking approaches for sustainability. Her research embeds understanding of environmental health risks. She's a lecturer at Camfield University, UK. Today's talk is a development of water management infrastructure and health impacts. Dr. May, anytime, please feel free to start. Thank you.
Thank you very much, Morris. Is my slide visible?
Yes, it is.
Okay. Thank you very much for the invitation to be part of this webinar. Good afternoon, good morning, good evening to everyone, depending on where you're joining us from. I'm conscious of the fact that we've taken more time, so I'll try as much as possible not to linger on as I go through my presentation. It's been very interesting listening to the other speakers. I think quite a number of them have touched a bit about what I want to talk about this afternoon. So my title is Development of Water Management Infrastructure and the Health Impacts. And a lot of this work is attributed to the Global Schistosomiasis Alliance Engineering Working Group, of which I'm the chair, and the work that we have been doing to try and highlight the importance of health when you're developing water management or water resources infrastructure. So just a brief outline here. I will talk about schistosomiasis, the water links, the impact of water resources development infrastructure, the elimination ambition, as well as key engineering and snail control measures. So what is schistosomiasis, which is bilharzia? I'm sure many of us are aware of bilharzia in Africa because Africa has 90% of the disease burden of bilharzia. And this is a disease, infectious disease that is caused by water snails, freshwater snails, as you can see in this picture here. What happens is when humans come into contact with contaminated water, the larval stage of these snails penetrate the skin and find their way through the bloodstream to the intestines, to the bladder of humans. And as such, we end up having the disease bilharzia. It causes high morbidity. A lot of children suffer as a result of it. It reduces their cognitive development, and we also have issues of cancer and liver failure as well. And this disease, there are about 200 million people infected worldwide. There are about 800 million people who are at risk, and most of them, 90%, are in sub-Saharan Africa. So the transmission, as I've explained, it goes through. So when the eggs are laid in the bladder, in the intestines, what happens is, if somebody defecates or urinates, those eggs find their way into the water body. And again, it hatches into the saccharia and penetrates another human. So it's a vicious cycle of transmission that goes from the human host to the snail host and then back to the human host again. And because of the huge economic impact and disease burden of schistosomiasis, we know that there are ways that you can control the disease. And one of the ways is by introducing the drug, which is called praziquantel. And this drug will be able to destroy the paired adults that are in the bloodstream. We also have the toilets that we can introduce to stop washing away of eggs into the water body. Professor Esaias mentioned wastewater pollution. So when we have fecal pollution that goes into the water bodies, our freshwater bodies, then the disease continues to be transmitted. If we want to destroy the water snails, most times we use molluxidine, but molluxidine has a negative impact because of the consequences on their environment. So it's supposed to be used with caution. Then finally, we want to destroy the saccharia. We introduce adequate water supply so that people do not come into contact with the water bodies that are contaminated. But that is a huge problem. Even when you provide water supply to people, because of other avenues or other means of contamination, especially through agricultural means, water contact activities, swimming, it means you're not really able to completely eradicate the disease or eliminate the disease. And as such, we know that in Africa, we have a lot of open water bodies where people come into contact with water. For example, you can see children here swimming in the water. You can see children here collecting water. So there's that exposure. The pathway to exposure is very difficult to break with just adequate water supply. And one of the problems, again, is water management infrastructure. So that brings me to what this session is all about. Dams and water management infrastructures are great. We use them for water supply. They're good for agricultural expansion and intensification. We use dams for hydropower generation. We use dams to prevent saltwater intrusion. But in these days, especially with climate change, we know that dams have also constituted a problem. And there's increased flooding now, which means you have more transmission sites of the snails. And the downside, again, from climate change as well, is when you have more drought and increased temperatures, which means you are having more water contact. And with dams, the main problem now is that people come into contact through irrigation. When they're in their farms, you can see here, when they're irrigating crops, they are in contact with the water that is contaminated. And so the impact, the positive impact of having a dam or increased agricultural intensification is the health impact. I'm happy that Professor Fateh mentioned the impact of health, and also when Professor Ali Homa was mentioning the water, energy, food, ecosystems, and health nexus. So not neglecting the effect that water has on health, especially on infectious diseases, is very, very important. And those undesired consequences of water infrastructure on health have been well documented. We know it clearly. There's so many researchers that have gone out to try and understand the impact of having dams and the implication on the increase of bilharzia in the communities that live around those dams. A classical example is the Derma Dam in Senegal. When it was constructed, there was hardly any cases of schisto. It was minimal. But once the dam came into operation, you can see how the cases of schistosomiasis increased remarkably, tremendously, from when the dam was constructed to about 10, 20 years after the construction of the dam. And this has become a very huge problem now in Senegal and other places where dams have been constructed in Africa. The reason is because when you have a dam, it means you have less or no prawns around the area. And those prawns are natural predators. So you have less prawns, you're going to have more snails. And snails are the intermediate host, which means you end up having more disease. If you have the dam, you have more water, and then more water means you have more people. And when people migrate towards the water bodies or the water management infrastructures that have been constructed, people can come in with the disease that they are coming from their various locations. And when you don't have adequate toilet facilities, you don't have adequate wastewater treatment, then it means that all the fecal waste is washed into the water bodies again. And then you eventually have more disease transmission. When you have more water, you have more agriculture, which means you're having more agrochemicals, which leads to more vegetation, and then more snails again. And then, of course, you have more disease. So the schistosomiasis of bilharzia is so intertwined with dam infrastructure. And so a lot, again, has been published. Researchers have published a lot of this in terms of mapping snail habitats and linking that to man-made water bodies. It is in existence in freshwater bodies or natural lakes, but the disease is exacerbated when you have the dams or other man-made water infrastructure also constructed without adequate still management in place. And so what do we want in terms of schistosomiasis elimination? The WHO has come together and has put forward a guideline on control and elimination of human schistosomiasis. And one of the recommendations, which is recommendation 5, is to have WASH, which is water sanitation and hygiene interventions, environmental interventions in terms of water engineering and focal snail control with molluscites, and behavioral change interventions as well. And a strong recommendation is having cross-sector coordination, multidisciplinary research, and building sustainability and resilience. And so how do we do that? We're working together, Cranfield University, with the African Ministers' Council on Water, as well as the Global Schistosomiasis Alliance, to look at how we can put together a document and a guidance for African countries so that they are able to control the explosion of snails around dam infrastructure. This is especially very important because Africa has 2 years ago come up with the African Investment Program on water to be able to leverage about $30 billion for water security and sustainable sanitation by 2030. And a lot of this money will be going into dams development, into irrigation schemes. And so to be able to ensure that adequate environmental impact assessment and health impact assessments, in addition to the recommended engineering control measures, are in place when a lot of these projects will be constructed. And that's the main goal for the Schisto Alliance, as well as for the African Ministers' Council on Water on the project we're working together. So the key control measures that we have identified so far is looking at flow regulation, dredging, habitat modification, concrete lining of canals, looking at drainage projects, irrigation canal management, maintenance of networks, and introduction of predators. And these have shown to have worked very well in Japan and in China. So it's taking on global examples, as well as a couple of African countries like Egypt and Morocco that have succeeded in reducing drastically the effect of schistosomiasis in those communities, in their communities. And we're also considering interventions before the construction of dams and other water management infrastructure, as well as interventions for existing dams to manage and mitigate the transmission risk. And we have put together some recommendations, and those recommendations include at the design phase, what is expected? How can we put in measures that will mitigate the explosion of snails and reduce the impact, the negative health impact that dams and irrigation canals, other water management, or the man-made water bodies can have? At the construction phase, what can be put together? So for example, at the construction phase, we're recommending having concrete banks construction, having natural predators introduction, and having concrete lining of canals. At post-construction phase, we are recommending dredging, health promotion, as well as improving access, overall access to water and sanitation. And at the operational level, we are recommending ongoing monitoring and maintenance, especially in terms of surveillance, so that we're aware when a problem is, it looks like it's going to be a problem in certain locations. If there is no surveillance, you will not know if there is a problem. But with adequate surveillance, monitoring and ongoing monitoring and maintenance around those communities that are within the catchment of those dams, where we'll be able to track and be able to have measures in place adequately that will stop the transmission of the disease. We are also recommending community education and outreach programs, and also water flow regulation at the operational phase. And so these are recommendations that we have put forward. And the African Ministers Council on Water as well, we are working using questionnaires with the 55 member states to try and understand how this can be translated into projects, ongoing projects or future projects based on the African Investment Program on water that is currently ongoing. And that is that. So this hopefully has kind of given you an overview of schistosomiasis and the linkage to dams and what can be done to be able to mitigate the impact of man-made water infrastructure, dams, irrigation canals, on reducing cases of bilharzia or schistosomiasis. Thank you. And that's my QR code for my LinkedIn in case you want to link up with me, and my email if you want to send me an email message to follow up with any questions. Thank you very much.
Thank you, Dr. Maiso. Very interesting talk. So I think just looking, people are still doing some interaction on the Q&A. Myself have a quick question. May I know, so this is, well, okay, so again, I'm not in this field in particular. It was interesting to me to see that, you know, building the dam have this direct influence on the health issue with this snail fever. But I was intrigued to see that not everywhere you build a dam, it will trigger this problem. Is there any, you know, some sort of explanation, for instance, why North Africa, although we have a couple of dams, you know, around, I say we because I'm originally from North Africa. And I also notice in other places such as, you know, whether in US or Europe. So is there anything that you could mention to me to just kind of understand the overall picture? Like is there something that triggers that, particularly in Africa?
Thank you very much for your question. That is very clear that in some places it's endemic in some locations, while it is not endemic in other areas. So mainly in tropical areas, that's where you have the endemicity of schistosomiasis, and the snails have been native to certain areas. The host snails are native in certain locations. But you can also have the migration where somebody from one location, they've had instances in the Costa del Sol's area, for example, where migration, people have moved from countries in Africa to those locations, and they have come with the disease, and have introduced it in some communities. So it's the fact that those snails are native to Africa, and Brazil, China, the areas where they have originally been habitat.
Okay.
So that's why it's mainly in those locations. In North Africa, in Egypt and Morocco, it was highly endemic at a point, but they have successfully been able to reduce or eliminate the disease because of the control measures that they have put in place.
Okay, so what kind of control measures? Just briefly, because I don't want to take too much time, but it's just intriguing to me.
Okay, so the control measures, aside from the ones I included in, so so you have the drugs administration, the praziquantel that I mentioned. So that is, it's quite expensive if you want to introduce praziquantel to the whole population, but it works. The downside is that it is not a vaccine. So if you prescribe or somebody takes praziquantel and they are okay, they are well, if they go into the water again, they'll get contaminated and there's reinfection. So that's why the drug in itself is not sufficient. Then if you have toilets and people don't use it, then you have universal sanitation coverage and people don't openly defecate, the feces are contained, there's adequate wastewater management, then you will not have water flooding or rainfall washing the eggs of the parasite into the water bodies. So you're able to break transmission in that way. And when people have adequate water supply, they're less likely to go into contaminated water bodies to collect water. So that way, again, you're succeeding in reducing or breaking transmission. In terms of occupational use, like for irrigation, the use of personal protective equipment like gumboots to stop the skin from coming into contact with water is recommended. So those are the control measures that can be put in place for the disease to be adequately eliminated, as we have seen in Morocco classically, and also presently in Egypt in their move towards elimination.
Interesting, interesting. Well, thank you so much for clear explanation, at least for a non-specialist like me. I think given the time, Dr. Meso, thank you so much for your contribution and for being with us here. I encourage everyone, please do contact Dr. May for, if you would like to interact any more with her or would like to collaborate with her. Thank you, May, again. I'm going to move to our last talk is, so let me make sure, Asma is here. Asma, please get ready to share your screen. So Ms. Asma is, hello. So Asma is a PhD candidate in Earth and Geo-Environmental Science at the Science Faculty of Ibn Zohar University. Before coming to Ibn Zohar, she completed 2 postgraduate programs in agriculture engineering and Hassan II Institute, and also Master of Science in Organic Agriculture from Bari, Italy. So she also holds a advanced specialist course in innovation and youth entrepreneurship in the Mediterranean agri-food sector from Shiam Bari. I would like to welcome Asma today to present to us a topic which I would assume from her PhD topic, enhancing citrus irrigation efficiency in Morocco's semi-arid regions. Asma, please, you may start anytime you want. Thank you.
Thank you, Dr. Moez, for the presentation. Can you please see my screen right now?
I think is, yes, now I can see it. You can maximize and then start. Thank you. Thanks, Asma.
Oh, no, we're good.
Yes.
I'll be presenting my PhD topic related to my PhD topic, which is in water management in agricultural water management. And basically, I am focused in enhancing citrus irrigation efficiency in Morocco's semi-arid region. So to do so, I will be stating the context of the PhD project, then the problematic, the scientific approach followed, and then the main results that we achieved. So previously, Dr. Ali Houma said that the Mediterranean region is actually facing water scarcity, and it is the case of the Moroccan Moroccan kingdom too. That will reach an extremely high level of water stress by 2040. And we actually already considered water stress with only 500 million cube of fresh water per capita, compared to back in times in 1960 when it was actually 5 times. So we're talking here about a global emergency, which is fresh water shortage that is affecting the Moroccan situation, just like any other Mediterranean country. At the same time, we have that we know that agriculture is directly linked to water in Morocco. Actually, it consumes more than 80% of the fresh water, and therefore food security is can be potentially affected by climate change. The climate change has also negative impacts on crop yields that actually been shown lately, and the changes in precipitation the affect hydrological systems, affecting water resources in terms of quantity and quality. So here we are directly related to two main goals of the SDGs, which are zero hunger and climate action. The problematic in our case, because we were more focused in Souss Massa region, which is a region where citrus is dominating because historically it has been developed and produced in Souss Massa in order to fulfill contracts for export. So we cannot actually, and we know that we are in a water scarcity condition, so we cannot actually ask farmers to take off or to change the crop adopted. So in order to find a solution, we're trying to mitigate and to offer a sustainable water management or sustainable management of irrigation water according to the crop needs. And in order to determine the crop needs, we actually worked on evapotranspiration, which is the response of the plant to the climatic demand. So our experimental site was in El Gerdam town in Souss Massa, which is in the center of Morocco, and it has a loamy sandy soil in a semi-arid Mediterranean climate with low and irregular rainfall. We focused mainly on the Isbal Clementine variety, and the system adopted is drip irrigation system. Though we all know that the drip irrigation has proved its efficiency, but we actually noticed that the strategy followed by the farmer tend to not benefit from the efficiency of the system adopted. So moving to the instruments, in order to quantify, as I said previously during the problematic, in order to quantify the water demand of the plant, we installed a decovariance station, which helps to quantify real evapotranspiration, and according to the sensible heat flux. Also, in order to pay attention to the deep percolation, which goes down to the soil, we installed like TDRs, which are recording soil moisture constantly at various soil depths, 2 at 5, 1 at 20, 30, 60, and then last at 80 centimeters depth. And the methodology or the theory behind is to ensure a energy balance closure in order to so we can benefit from the measurements of real evapotranspiration taken by the station. So the energy balance closure, as you all know, its component is the solar radiation, latent heat flux, and the soil heat flux also. So we have to find at the end of the measurements before actually computing real evapotranspiration values from latent heat flux. We have to ensure that we have a more than 75% closure. And also the second theory adopted was soil water balance. Actually, the TDR help actually sensing if we have deep percolation, especially at 80 centimeters. And in order to balance both, we have as an input irrigation and rainfall, and as an output actual evapotranspiration measured by the station of eddy covariance, and deep percolation that we compute as the difference. So for the results, basically, we, as I said previously, that all our energy balance closure, normally this should be higher than 70%, but in our case, like for 3 consecutive years, it was higher than 80%. The lowest value was 81, and the highest value of the closure was 87. And we can compute the evapotranspiration values from the latent heat flux. So for 3 consecutive years, real evapotranspiration was always like higher than 700, almost 800 millimeter per year, with a minimum of 1 millimeter per day and a maximum of 6 millimeter per day. And you can notice that when it's the evapotranspiration is high actually around July and August, which actually is known by high temperature, as you can see in the graph, and low values correspond to December and January, which actually correspond to the bud burst of the crop of citrus. And later on, from the evapotranspiration value, we computed crop coefficient values that are, we use the FAO 56 paper methodology that actually computes crop coefficients as the evapotranspiration, real evapotranspiration divided by reference 1. And we actually we noticed that our experimental crop coefficient ensure a 10% economy in comparison to the FAO model. So it's going to be 10% economy of water. And regarding deep percolation, for like the 3 consecutive years where we conducted the experiment, we noticed that every time the farmers tend to give a higher amount, sometimes the double of the amount required by the plant, which is actually gone, and it doesn't even bother like contributing to regenerate the water table, because we are in a sandy soil, and the water table is like at 150 meters below the surface. So in our case, we noticed that there is always deep percolation that is esteemed at 40% of the what actually the plant requires. So we can ensure a 40% economy of using the crop coefficient values that we developed in this experiment. And in order to help the farmers access the knowledge or the results that we elaborated, we developed an irrigation schedule according to the phenological stages. It's going to help farmers to know how much water to allocate in every phenological stage. And for like farmers that have like big farms and actually have like that have a minimum knowledge to compute the values of water requirements, we offer them the crop coefficients table, and they are adopting it right now. So in order to conclude, in this project, the study is the pioneer of the use of the EC technique, eddy covariance technique, in the region of Souss Mesa, and it is addressing the challenges of its semi-arid climate. We noticed that meteorological conditions similar to the Mediterranean area result in high reference evapotranspiration values, necessitating to supplement rainfall, erratic rainfall with irrigation. We developed a reliable irrigation protocol using the computed values of evapotranspiration and thus and also the crop coefficients values. And finally, the water saving by employing the FAO 56 simple approach, we suggest a significant water saving of around 55%. And sometimes it is less at 40%, but but it's going to customize drip irrigation schedule and highlight the importance of managing deep percolation losses through improved water flow control. That's it. Thank you for your attention.
Well, thank
And
you.
this is my email.
Well, thank you so much, Asma, for your presentation and for keeping it to, within the time. Okay, yes, this is the email. Anyone who wants to reach out to Asma, please do so. And well, of course, the professors who are looking for PhD students, please do so as well. And for postdoc position, please do so as well. Asma, is it possible, because I think there is attendees asking questions. Is Samuel wants to talk or not? I mean, I'm not so sure. Please write your questions if you have a question to Asma in the Q&A, or any of the panelists would like to ask questions. Asma, for a person like me who's not an expert in this field, in a layman language, would you explain to me how was, in a simple way, how did you save the water per this optimized per locations? Is in a very layman language, like, for somebody who's not expert.
So in order to, because we noticed that farmers offer irrigation according using the coefficient of FAO Penman of FAO 56 paper. Sorry, they were using those coefficients, and we decided that we noticed that because we installed the sensors in the soil, that water was actually leaching. So it's a water loss that the plant doesn't need or benefit from, and we actually do not have to supplement it. So what we do is that we quantified how much the plant is actually needing according to the response to the climatic demand, and we divided through the reference evapotranspiration, which is related to the to graceland or to reference crop, which it can be also alfalfa. And the difference, the average, actually gives a coefficient that we call crop coefficient. And according to this crop coefficient, we developed a general protocol in the phenological stages. I hope I was clear.
No, that was much more clear, at least for me. Maybe also as you're speaking, maybe difficult to catch up. Thanks so much, Asma. So it's gonna be crop dependent. So it depends what you are planting. The coefficient would be changing, how much water and how much they need. So it always has to be recalibrated, right? Is there anybody wants to? I think there's a question. Asma, how do we expect deep perlocation from drip system as such? Do you have? You can read the question as well. You can read the question in the Q&A if you would like. So Asma, they're saying, how do we expect deep percolation from drip systems as such?
Because the strategy, I know it's a really huge amount, like 40 to 55 of water, because it's a huge amount of water that is lost. Why do we expect it from drip irrigation? Because the strategy adopted by the farmers is not adequate. We're not doubting the drip irrigation system here. We are just questioning the strategy followed by the farmer.
Okay, so another question, follow-up question is, why is your KC values are lower than that of FOA in all cases. And this give you a good training for your defense, I would assume, right?
So yeah, it's actually near. So yeah, I have to be prepared. So the KC values in our case is lower because of the climate. The FAO were actually in another climate. In our case, they are like suitable for the climate of Mediterranean. If you notice that there are other studies like the same in Morocco actually that are in the Tel Sift basin, and they were actually lower than ours, though it's almost the same climate. So they all depend every time on the meteorological conditions and the climate of the region.
Well, thank you. Thanks, Asma. Maybe one last questions. I'll just read this one. How did you determine the experimental KC? Did you use a lysimeter? Honestly, I don't know this instrument or what. So
No, we didn't use a lysimeter. We used anidi covariance to determine the evapotranspiration, real evapotranspiration values. And then we calculated through a meteorological station, we calculated real reference evapotranspiration soil. And we divided real evapotranspiration by reference evapotranspiration according to the FAO paper. This is the equation. And we developed like simple prop coefficient values.
okay, thanks so much, Asma. I thank you again for your contribution and for joining this event. I would like to thank everyone and all the attendees for joining this event and all the speakers for today's session. I would like to share my screen just to let you know that we will have the next upcoming session for the Africa Scholars Meeting will be on the 13th of May. If you are interested, please do join us. We'll have 4 speakers for the next session. And I would like to remind everyone about the upcoming Africa Congress. Please save the date. If you came late, you did not hear about this. The Africa Congress will be from 9 to 12 of December. This is a QR code for the website is open for registration and abstract submissions. With this, I would like to again thank everyone for their contribution, for attending the session. I look forward to seeing you all in our next session. Take care and have a good day everywhere you are. Bye-bye.
Thank you so much. Bye-bye.
Thank you so much. Thank you all.